Mm.
Thank you for the invitation. So I will be talking about manifestations of young neutron stars. Uh, so I'm not doing this in isolation. This is a part of a TÜBİTAK project, and we are collaborating with many colleagues here. But in the project, we work with Dr. Sinem Şaşmaz and my PhD candidate, Fahrettin Ay. But I will be mostly talking about what we have done with my colleagues before. So first, I want to give you the picture of neutron stars until 1990s. Okay, there were the radio pulsars, which were understood to be rotationally powered. So this is the spin down luminosity of the radio pulsar. But of course, the radio power is a tiny fraction of this spin down power. On the other hand, we had these X-ray pulsars, which we understood to be gravitationally powered. So here, in this case, there's a disk around the neutron star, or it's accreting from a wind, and then the matter reaches the magnetic field lines, coupled to the magnetic field lines, and finally ends on the polar caps. And if this hot polar cap is passing from our line of sight, we see the pulses. But today, we have anomalous X-ray pulsars, soft gamma ray repeaters, central compact objects, X-ray dim isolated neutron stars, rotating radio transients, and high magnetic field rotationally powered pulsars. So how do we understand these, right? Where will we place them? And most importantly, the supernova rate in the galaxy is not sufficient to produce each family separately. So there must be some evolutionary links between all these young neutron star families. Here, of course, you see these gorgeous Crab Nebula, which is the remnant of the supernova that exploded in 1054. And at the center of this is the Crab pulsar, which is rotating with its frequency with a period of 33 milliseconds and with a period derivative about 4 times 10 to the minus 13 seconds per second. And this, remember, corresponds to a spin down about microseconds in a year, right? And this is still too much power, which is much greater than the luminosity of the sun, okay? And we also know that the pulsars have large velocities, and this Crab pulsar also has a space velocity like 140 kilometers per second. And this object is radiating from radio to gamma rays. So in all bands, it's very active. At the inner parts, you see the Pallerion, which is a magnetized wind of charged particles accelerated to relativistic speeds. And this is the hallmark of this pulsar action. And there's non-thermal emission can be seen from this radio to gamma rays. And in the high gamma range, you can reach up to 100 tera electron volts. And our model for this, the simplistic caricature model, is that it is tapping this energy from this rotational kinetic energy, and it's doing this with magnetic dipole radiation. So this is a spin down of the form minus k times omega cube. And from this, it is possible to estimate the or infer the magnetic field of the object, which for the Crab pulsar we find 4.4 times 10 to the 12th Gauss. And the characteristic age, which is a ratio of period to period derivative, would be of 1,240 years. And comparing this to the true age, we see that this model works quite fine. And you can also solve this equation, but the result is very obvious, and it says that the life of a rotationally powered pulsar is determined by the initial spin period and the magnetic moment. But this is a very boring picture. There's no place for anomalous X-ray pulsars, soft gamma ray repeaters, central compact object, the magnificent 7, and the rotating radio transient. So we should go beyond this simple picture if we are to understand all these objects. If you look at the period derivative diagram, you see that some objects with similar period and period derivatives just behave differently. So this is not sufficient to understand the properties or diversity of these objects, neutron stars. And you see the surface magnetic fields and periods. There are overlapping regions in this diagram. So it is also telling us why is this so. If we go to the rotationally powered pulsars, we have a good observational handle, which is called the breaking index, which is a dimensionless number, which is omega times the omega double dot divided by omega dot square. And if the rotationally powered pulsars are spinning down under magnetic dipole radiation torques, you would expect this number to be exactly 3. But the observations show that, well, it's not quite 3. Well, there are instances where it approaches 3, but it's not exactly 3 in any case. Some of the explanations proposed for this are as follows. Well, one is the relativistic particle ejection. Well, this is observed already, right? There are relativistic particle ejections, but will it explain all of these breaking indices? That's the question. The changing moment of inertia. Remember, as the neutron star is born and it's cooling down, the superfluid components will change in size, and this would lead to a changing moment of inertia. And this could cause this break-in indices. Was proposed in 2012. Another suggestion was by Andrew Melato, saying that the pulsars are not point dipoles because of the presence of this co-rotating plasma. We need to consider the non-point effects, which would change the value from 3. And of course, there could be propeller torques by fallback disks. Another idea is that the magnetic fields of pulsars are growing in time, and that would change the break-in index from 3 to lower values, noting that nu dot is a negative value. But why would the magnetic field grow? Well, there are different suggestions, right, by thermoelectric effects and thermomagnetic effects. And another interesting suggestion is that the magnetic fields are buried in the first place because of huge accretion by the supernova fallback matter, and then it rediffuses to the surface in time. That's leading to a growing magnetic fields. That was suggested some time ago, and it's still being worked out. Another issue is that this vacuum, the dipole model has other torque components. Well, one component is the spin down component that we have already mentioned, but there is another one, which is the alignment component. Okay, so it's expected in theory that the separation between the rotation and magnetic axis will be decreasing in time, and this is going to lead to breaking indices even greater than 3. And this was noticed in 1970, soon after the discovery of the pulsars. And the hope was that there's dissipative processes in the crust will be delaying this alignment so that we can observe the pulsars. In the presence of a rotating plasma, it is shown that the breaking index is still greater than 3, but somewhat between 3 and 3.25. And the alignment process becomes slower due to this effect here, 1. And in 2016, there was a finding that the breaking index of this pulsar J1640 is slightly greater than 3, and this found a natural explanation in the presence of this alignment torques with the plasma field case. This alignment torques contribution was neglected by the original discoverers of the breaking index because they used the vacuum model, which is estimating a very huge breaking index. But with this, we could just show that the breaking index could be explained nicely with this. But so this is the maximum value the breaking index would get under magnetic dipole radiation torques. So we still have to face the problem with the lower than 3 breaking indices. And with this model, by the way, the equimagnetic field lines are no longer straight in a log-log plot. They would be tracing these regions. Now, let's go back to the young neutron star families, right? The first family I want to talk of are the soft gamma ray repeaters. They were discovered when they showed these bright short bursts. The bright bursts were, about 10 to the 40, 10 to the 41 arcs per second, but these were happening within a milliseconds range, sub-seconds, let's say. So they were first considered to be gamma ray bursts, but then soon they understood that they had a softer spectrum and they were repeating. No GRB had seemed to be repeating. So astronomers have quickly understood this is something different. And they also observed the giant flares occasionally, especially this, the first event is this one in 1979. So they were facing a phenomena related to neutron stars. They've seen the pulsation periods and they understood this is something different than the gamma ray bursts they have been observing for a long time. Okay, another object here was observed through its soft X-ray spectrum. Okay, with it has a large period of 7 seconds. It is showing X-ray pulsations, but there's no binary companion to provide accretion matter. But it was classified as an X-ray pulsar. But of course, this anomalous behavior was noted, so it's called anomalous X-ray pulsar. It is always spinning down, and that is really strange because accreting pulsars sometimes spin up, right? So this, then you could think about things like rotationally powered pulsars, but you cannot, because in this case, the X-ray luminosity is much greater than the spin down luminosity. So it cannot be rotationally powered. So anomalous X-ray pulsar is the name given to these objects. And we find that they have similar properties with soft gamma ray repeaters, similar spin and luminosities. So people noticed that they could be close relatives to each other. So anomalous X-ray pulsars and soft gamma ray repeaters together, they would have the following properties: spin periods about 1 to 12 seconds, and their typical ages are very young. This young age also is indicated by their proximity to the galactic plane and the association rate of the supernova remnants to these objects. When you go to the rotationally powered pulsars altogether, the relation to supernova remnants, association with a supernova remnant is very rare, only 10% or so. But here you see 1/3 is associated with a supernova remnant, indicating that these objects are young as a group. And very recently, a 300 years old object has been discovered. So this is a very strong view that these are very young objects. Anyway, their persistent X-ray emission is about 10 to the 35 to 10 to the 36 arcs per second, which is always greater than the spin down luminosity. They show the sub-second duration X-ray bursts with peaks luminosities reaching 10 to the 41 arcs per second, which is the definitive property of these objects. And on rare occasions, there are more extreme events, which we call the giant flares, right? And there are intermediate flares also. So they reach or they release energies like 10 to the 44 or 10 to the 46 arcs. And they occasionally show radio pulsations at the spin period or some individual radio bursts. And first of all, there were accretion models for anomalous X-ray pulsars when people thought they were X-ray accreting objects. They made accretion models, of course. And accreting neutron stars with very low mass companion was proposed. So they could not see the modulation due to the Doppler shifts. So this is showing that these objects are isolated, but probably they thought there could be a binary companion which we cannot detect. Single neutron stars accreting from a disk formed by remnants of the common envelope evolution of high mass X-ray binary. That was another suggestion in the 1990s. And in the beginning of 20s, the fallback disk model was proposed by Ali Alpar and Charity Hanquist and Narayan. But the most widely accepted model for anomalous X-ray pulsars and soft gamma ray repeaters is that they are magnetars. That means they are objects with magnetic fields exceeding the quantum critical limit, which is about 4.4 times 10 to the 13 Gauss. And this was stimulated by the exceptional giant flare of 1979 of this soft gamma ray repeater. And discovery of the rapid spin down of the object by Kuiletu and her friends imply that they indeed could have such high dipole fields. And magnetar model it has two magnetic fields accordingly. The external magnetic field drives the angular momentums by the magnetic dipole radiation and pulsar wind, just like it happens with the rotationally powered pulsars. The magnetar events are related to the huge toroidal magnetic field inside the crust. And the bursts of sub-second bursts of 10 to the 38 to 10 to the 41 ergs per second would originate in sudden energy injections resulting from the crust quakes. And a persistent X-ray emission of 10 to the 35 to 10 to the 36 ergs per second would be released by the gradual untwisting of the magnetosphere. And the giant flares would originate from the reconfiguration of the inner magnetic field or the magnetosphere instabilities. Now, let us look at another extreme object, Cas-A, which is about 300 to 350 years old, depending on who had seen the supernova explosion first, Cassini or Flamsteed. In this case, there is a neutron star at the center, but not acting as a rotationally powered pulsar. For example, there is no pulsar with nebula, okay? Some of these objects show some X-ray pulsations with periods of 100 to 400 milliseconds, but there are no counterparts at any other wavelength than the X-rays. And they would have luminosities 2 orders of magnitude smaller than the anomalous X-ray pulsars and soft gamma ray repeaters. Some would have 2 black body components. And the spin down rate together with these periods indicate to a very low magnetic fields compared to the population of rotationally powered pulsars, 10 to the 10 Gauss. Yet the high pulsed fraction imply that there is a peculiar thermal isotropy on the surface of these objects. Why you would have such high pulse fraction although you have such small magnetic fields? Why is this temperature distribution not very uniform? Up to date, about a dozen central compact objects were discovered, but since they are hard to discover, unless you need to find a supernova remnant first, and then you have to look at a center to find a neutron star. If it is not acting like a rotationally powered pulsar, or it doesn't show the magnetar burst, then you would just say this is a central compact object. The low dipole fields of these objects, together with their high pulse fraction, indicates to the presence of very high multipole fields. Is this a result of inefficient dynamo mechanism that is suggested for the magnetars? But this cannot explain the peculiar thermal anisotropy. Somehow the magnetic field must have been generated. Another suggestion is that they are quiescent magnetars. Well, one of them indeed showed magnetar activity later on. Now we qualify it as a magnetar, but it is, it was already strange at the beginning that that object had a very long period, like 6 hours, not observed from any other neutron star. I am talking about the bulk of these objects, especially the ones whose properties we know, which is rotating with 100 to 400 millisecond periods. Yet another suggestion is the field burial scenario, which is saying that some fraction of the material ejected out in the supernova explosion returns back and falls back onto the neutron star and buries the magnetic field under the crust for a while, and it takes about 10 to the 3 to 10 to the 5 years for this field to re-emerge or diffuse to the surface. So these non-uniform surface temperatures indicate to strong crustal fields, and they could have buried magnetic fields. This is being explored, and this amount of matter accreting could be one parameter that is making the diversity in the neutron star family. And here is a pertaining question: is the neutron star, putative neutron star that formed in the supernova 1987A, a central compact object? Is it its field could have been buried, and it might be expected that the pulsar will activate later on. That is an idea suggested very early. Another group of objects possibly related to the magnetars are the radio-quiet X-ray dim isolated neutron stars. They show pulsation in X-rays. They have periods matching the periods of the soft gamma ray repeaters and anomalous X-ray pulsars, but their temperatures are lower, and their estimated magnetic fields are an order of magnitude less. So they were first discovered also in 1996. Now, why would there be any field burial if this is indeed working? Consider a star at the brink of core collapse. The sound crossing time for the object will be twice the radius divided by the sound speed, and this is about a few hours. But the free fall, the collapse, happens within seconds. So there is no way the collapsing component will be able to sample how much mass is overlying it, so that it should release a certain amount of energy to expel it all to infinity. And in all supernova models, we have some fallback material accreting back onto the neutron star. But the question is whether this is going to bury the magnetic field. Well, we better say that it will not bury the field, but make it a tangled one with very complicated tangled magnetic fields. And the following evolution will be the merger of these tangled fields to become a dipole field altogether. So effectively, the dipole component will be growing in time. Now let us see how we can test this model. We know that the pulsars are also born with very large space velocities, right? 100 to 1,000 kilometers per second. Although we know the progenitors of these objects have much smaller velocities. So it means that the pulsars get kicked, and possibly this is because of the asymmetry of the explosion. Now, if there is accreting material onto the newborn neutron star, and the neutron star is moving in this medium, the amount of matter that will be accreted onto the neutron star will be affected by this velocity of the neutron star. If the velocity is large, the mass accretion rate will be smaller. And that means the following: if the neutron star gets a large kick, delta M, that is the amount of mass accreted onto the crust, is small. And if this is small, the field growth time will be short, simply because there's a thin layer. Okay, and if the velocity is large, then this this is going. If the velocity is large, we can then combine these to see that the field growth time will be short because the field is buried in a shallower layer. And this idea to test the model was proposed by my student Abdullah Güneydaş and me in 2013. The unfortunate thing is that there are few pulsars which have both measured breaking indices and space velocities. So we can estimate the field growth timescale from the measured breaking index and then see the relation to the space velocities of these objects. And this marginally supports indeed the view that there could be some relation between the space velocities and the field growth timescales. If the velocity is large, the field growth timescale is short. And recently, this pulsar has shown a change in the breaking index, right? And its position in the diagram is now here. This is also consistent with the model in a better way. So this is a model relating the breaking indices to the pulsar speeds under the framework of field burial model. So let's talk about fallback disks now. What happens if fallback matter has some angular momentum? Then it will settle into a disk. This was proposed in the early 1980s and by Michael and Dessler. Avoiding their formation requires fine-tuning. Then why are they not very ubiquitous? But they are very hard to detect due to extinction in the galactic plane. And possibly in some cases, they are disrupted by the huge power transferred by the rapidly rotating magnetosphere. Some properties of the fallback disks would be as follows. They are one-shot disks compared to these continuously fed disks in binary systems. So when the disk is all finished, and it's all finished. The outer radius is not tidally truncated as disks in binary systems, but it expands freely until the disk becomes cold enough for being active, right? And one other difference would be the existence of heavy elements in these disks, which could change the opacity, for example. Conventionally, we have seen that the magnetic field and the initial period would determine the evolution of the neutron star if you don't consider any other effect. We mentioned that the velocity of the pulsar could be another parameter changing the life of pulsars. There could be, it determines the amount of fallback accretion in the beginning. And the initial mass and angular momentum of the disk might be additional initial parameters determining the evolution of young neutron stars. So fallback disks would add two parameters, two more parameters to the evolution of neutron stars, and could make the evolution of neutron stars, young neutron stars, more colorful. And it need not be an alternative to the magnetar model if the magnetar fields are in the higher multiples, as we have suggested some time ago. Now, the optical, infrared, and spectral energy distribution of 4U 142 is observed here. This was given in Wang, Chakrabarty, and Kaplan, and this is the first evidence for the existence of a debris disk around a young neutron star. But they argued that this disk they observed is a passive one, and in 2007 we have shown with our colleagues that the overall overall broadband data set can be reproduced by a single model with an irradiated and viscously heated disk, assuming that the data is deredent with this factor. And more recently, there was this infrared observed in the Vela pulsar, and Danilenko et al. Suggested whether there could be any fallback disk around this object. Their disk was beyond the light cylinder of the pulsar. The inner radius was way beyond the light cylinder, so it cannot play any role in the spin history of the Vela pulsar. But using these data as well, not on the F nu plane, but new F nu plane, we have shown that the spectrum could be explained by a quiescent disk model, which was first proposed by Sunyaev and Shakura in 1977. This is a work done with the Jena group in 2014 with my undergrad student, Gökçe Öztürkhan. So the disk is protruding the light cylinder in this case, and there are large propeller torques leading to the dissipation in the boundary layer at the innermost part. This gives the infrared, this gives the ultraviolet luminosity. And then there is this irradiated disk model, and the viscous disk can explain the optical part of the spectrum. So their combination is quite fitting with the results, observations, I'm sorry. But the fallback disk model is not favored recently, especially due to the noise properties, right? We have been observing X-ray pulsars and their noise properties for a long time. And recently, Cherry Serim et al. Have shown that the noise strength in these rotationally powered pulsars and the magnetars just are a continuation, right? Which is expected if they are, not accreting objects, but isolated objects altogether. On the other hand, if the magnetars are accreting from fallback disks, you would expect that the noise strength would be proportional to the X-ray luminosity, which is not observed, as you see here. So no correlation between noise strength and the X-ray luminosity weakens the fallback disk model accretion from fallback disks in the case of anomalous X-ray pulsars and soft gamma ray repeaters. Now, on the other hand, is this magnetic field alone sufficient to address the diversity of these objects? Well, there is evidence that the dipole field is not the single parameter leading to different manifestations. First of all, we observe low magnetic field magnetars. We observe radios from magnetars. Well, and we observe some rotationally powered pulsars to exhibit a magnetar activity. So it is just implying that the higher multiples of these objects could be important. So I come to my conclusion. Alignment torque is an intrinsic component of the magnetic dipole radiation torque, and it naturally explains the greater than 3 break-in index of J1640. And the field burial scenario implies anti-correlation of space velocity and field growth timescale. This is a question asked to the nature whether this field growth or field burial scenario is correct, and the answer is promising, although the number of data is very small, so it's just a marginal support. And So the recent transition of this object to a rapid spin down with a smaller break-in index also implies that is consistent with the proposed relation between space velocities and the field growth timescales. I thank you for listening, and if you have any questions, I'm willing to answer.
We thank Professor Kazım Yavuz EKŞİ for his talk, and I see one comment from Professor Ali Alpar in the chat panel, and he says that if fallback is present as invoked for B-field burial, one cannot get rid of angular momentum, so fallback disks must be present. Any comment on this, Yavuz Hocam?
Let me...
You can see the comment in the chat panel.
If a fallback disk is present as invoked for B-field burial, one cannot get rid of angular momentum. So fallback disks must be present. Yes, I think so. I mean, this is what is observed during star formation, right? The low angular momentum material falls onto the central object, the star, and the remaining materials, specific angular momentum increases in this process, and this favors the formation of the disk, and we know the planets form from such disks, right? So if this happens with the neutron stars, right, during the collapse, I would expect the formation of fallback disks, but whether they are, the source of persistent X-ray emission of anomalous X-ray pulsars and soft gamma ray repeaters is another question to be answered. I mean, it's not very clear from the observations. First of all, the noise relations exclude this. And I think it is, the luminosities and the period clustering is not very easy to obtain simultaneously, even with the fallback disk model. This is my suggestion.
Okay, and thank you very much for this comment. And I see no other question in the chat panels. And hereby I close the morning session of our workshop. And thank you for all participants and all speakers. And the next session, afternoon session, will start at 1:30 p.m. So until that time, we wish you have a nice